Yeah. Okay, let me start. Okay, should be recording. Let me just check whether it is recording right. Yeah. Okay, so first of all, I would request if anybody does not need to talk, please mute yourselves. Otherwise, some noise is coming. Please mute yourselves. You can see my screen. Let me check. Okay. Good. Okay, so today we will be starting our lecture on optimization mostly. So let us go straight. Okay, yeah. So let us go straight towards the to the agenda. Okay, now. Yeah. So yes, the agenda is understanding the basics of matrix and vector calculus and optimization concepts to be used in this course. But before even that, we will understand different types of errors in the learning. So basically, that is just some brush ups from the machine learning course, and mostly it is on from a little bit from the learning theory. Okay, give me just 1 second. Yeah. Now, so I'm just trying to make sure that if everybody can, yeah, that is better. See my screen. Yes. So this is the basically, yeah. So these are all the resources. So mostly the material I have taken from chapter 8 of the deep learning book, but as you will see, more and more as we delve into the lecture and even more into the course, things will be taken from many other sources, mostly many online lectures, other blogs, etc. And the respective sources will be given in this in the slides itself. Okay, now so we said that we are in a deep learning course, and I mean this topic is about optimization. So let us first try to see what are some connections between optimization and deep learning. What do we need? Why do we need to learn a bit of optimization for deep learning, right? So deep learning or machine learning in general actually involves optimization in many contexts. So I mean, first of all, our goal is to find the best parameters and for a neural network or any machine learning model. So to say, it can be neural network, it can be SVM, it can be random forest, etc. Now to find the set of parameters that is best in some sense, and best in what sense? It has to provide a minimum value to some objective or some cost function. So the cost function, how do we measure the cost function? So or what is the cost function or the objective? So for a neural network or any machine learning model, the cost function is measured in some sense of a distance from what we want to get and what we are getting. So you are given with some input and you would like to have some predicted output. So one example, typical or canonical example is classification scenario, right? So image classification scenario. So you are giving some input image and you have labels for that. Labels means what class does it belong to, say whether the image belongs to cat class or dog class, etc. So that labels you want to predict, and you have some gold standard, that is, you have the ground truth that, okay, this image belongs to cat class, this image belongs to dog class. Now when your model is trained, or you have your machine learning model is learned, then that is giving some predicted output, which is predicted level. So how these two match, that is the predicted level and the or how far these two match, the predicted level and the ground truth level. So some sort of a measure of match of these two, so how close they are. If it is a regression problem, regression problem, in regression problem you try to predict one or more scalar values, right? So a simple regression problem is predicting one scalar value. So you have the gold standard, the ground truth scalar value for a particular x. Say x is the input and y is the output. So suppose your for the same x, your predicted output is y hat. So how close is y hat to the y? So that gives you a sense of the cost function. So what is the cost of basically like how far away this your predicted your model's prediction from the ground truth, and that gives rise to the cost. So if it is more, that is the distance is more, then the cost is more, right? But this idea fits perfectly with the philosophy of optimization, because in optimization also we try to find, or rather with respect to a cost, we try to find the best set of parameters, as I'm saying here, the best set of parameters. So we try to minimize the cost by changing the parameters in a bit, or that come is related to one particular way of finding these best parameters, that is gradient based optimization. So mostly we will resort to it. There are other ways, not only just gradient based. There are ways where you don't need to even compute the gradients, which are evolutionary or derivative tree optimization. But they have advantages. Sometimes the cost is such that you cannot find it may be discontinuous, so you cannot find, say, a gradient. So in that case that helps, but it comes with its own issues also. So they are used in machine learning, but at least they are, for some certain models they are useful, but at least for neural network they are not known to give too much advantage, and we will not go into that at all. So we will resort to only the gradient based optimizations, at least for the purpose of the course, and we will see different types of gradient based optimization itself. It is you can see that it is very easy to spend one, if not a couple of semesters on optimization itself. And what that means is that if we plan to cover this in 2-3 lectures, we will only scratch a small part of the surface. So yeah, so this is about, again, a very brief type of description of the connection between optimization and deep learning. And summarizing it is that optimization also deals with minimizing a set minimizing a cost function, or maximizing an objective. So if it's a maximization problem, then we sometimes call it as objective. If it's a minimization, then it is cost or risk. They are interchangeably used. And in deep learning also, or rather machine learning also, we try to find a set of parameters that significantly reduce a cost function or objective function j theta. So this is again on a high level the connection between optimization and deep learning. Now let us having seen the brief connecting link between optimization and deep learning, let us see some important differences between the two, and that is crucial. So in learning, or specifically supervised learning, so we have two sets of or two different sets of data. So the training set and the test set. So so for example, if you take image classification or language translation is another application, where image classification, I said earlier that input is image and output you want to have the label. And in case of language translation, what happens is that you have a sentence in one language, say in English, and you want to get the translated version of this sentence in, say, some other language, say French. So you care about some performance measure, of course, that how good your model is. And I mean, for image classification, the performance measure is accuracy. Okay, you have a set of held out data that, okay, these on which I want to basically compute the I want to test how my model performs. So for that, what you will do is you will find that out of say you have 100 such test data. So you will see out of these 100, how many you are getting the correct level. So that is your accuracy. And there are other measures we will see, the top 1 accuracy, top 3 accuracy. Top 3 accuracy is whether it is giving, I mean, the model is given a chance of predicting, say, 3 guesses. Okay, for one image, okay, what is the most likely level you want to give or predict? What is the second most likely, third most likely? If whether the ground truth comes, or whether the model is able to at least predict the right level or right class of the image within the 3 guesses. If it is able to do it, then we say that, okay, I mean, it has achieved the objective. So what I mean by that is that we will take it as one example which is top 3 accurate. So how many such examples out of these 100 you have top 3 accurate, that will give you the top 3 accuracy, so on. And we will see several other measures for different applications, detections, etc. They have different measures. For language translation, how good is it is matching with the actual translated sentence, translated by, say, some human. So so we care about some performance measure on test set. So the important thing is we care about this on test set. But when we minimize or when we train the model, we minimize the cost function j theta on training set. And why? With a hope that doing so will improve P on test set. So P on test set, right? So why can we not basically minimize the cost function on test set? Because we don't have all the information for test set. For measurement we have, but we are not allowed to use, because that is the goal of the machine learning problem, and that is where it differs from optimization, right? That you are given with some I mean, given with some data with all information. So by all information, I mean the for image classification scenario, images, corresponding levels. For language translation, sentence in English, sentence in French, and so on. So so you have that, and then you are expected that your model will do good on some unseen data. That is the test set. So you are given access to all the information in training set, and you are minimizing the cost function on there, but your hope is to get good results in P. But that is the different thing in optimizing. In optimization itself, I mean, just minimizing the cost function is the objective, and you get the best set of best parameters. So the catch is that optimization procedure minimize the cost for the training set, as I said, and I mean, sorry, yeah, machine learning models, the optimization procedure minimizes the cost for the training set, so that we predict this good in the test set. This is simply because we have the output information of the training set only. That is, we don't have access to the all the information in test set. And we hope that the good parameters for training, or good parameters that come out by minimizing the training set will be as good as the for the test set too. So that is just the hope, and this is in contrast to this pure optimization, where there is no question of such hope as we minimize what we want to minimize. Okay, so yeah, so the next thing we will see is that let us see what types of errors creep in as a result. So this is the major difference with optimization and deep learning. So as a result, of course, due to this hope that okay, it will do good in test set, even though we are minimizing in training set, there are some errors that creep in. So we will discuss about it next. But before that, if you have any questions on this brief part, please ask away. Okay.
From optimization, you said that we hope in normal machine learning, but in optimization we have a goal. But I see that both of them have a goal, matlab to minimize the error.
Both of them has a goal, but the goals are different. So the goal ends in optimization by just trying to minimize the optimization object. You want to go to a minima, you want to get some best set, the minimizing argument or the maximizing argument for a maximization case. But in optimization, in deep learning, what you do that in the training set. But the hope is that you do, I mean, you don't, I mean, what the problem creeps in for that, if I tell that, maybe that will make it more clear. So suppose you are minimizing the cost function for image classification scenario in a say with for say autonomous driving scenario, and your training images are coming from say daytime images. So you are sunny day. So your car that collected the training data was driven in a sunny day scenario. So you get pedestrian images, tree images, animal images, etc. Even the road signs, etc. in the daytime scenario. So you minimize it very good. Your if your test set is actually coming from exactly the same scenario, a sunny day on the same place, etc., maybe the same season, it works good. Okay, but if it is say snowy night, so foggy night, it may not do good. But your expectation is that that the test, the whatever model you have learned using the training set, it will work good in test set, whatever may be the test set. Of course, the scenario is, I mean, the application is same. You may not expect that okay, you have trained it on classification and it will work good on detection, not that. But even in the same application, but if just the domain of the data changes, then it's a problem. And that's an important problem in machine learning. That's called the domain adaptation problem. So you need to adapt to say different domains of data. So what you said is true, that in optimization also we want to minimize an objective, but the slightly subtle catch is that you minimize it in machine learning. You minimize the objective. You minimize the objective in both the cases. In machine learning, you minimize it using a training set, but expect that it will do good on the test set. So that is not there in optimization. That it will have to work on some other set which may or may not be similar to the training set. Right. So that's sort of the difference. Any other questions? Okay, if not, let us go ahead with this expected and I mean all these errors that can creep in. So let us now try to introduce a few notations or things that we need throughout the course. that is training data. So let's say training data is given by these tuples, that is X and Y. I means the ith example. So there are n examples in our training set. That is, you have n training data for which you have both the input and the output, the ideal output. So X is the input, Y is the output. Now, coming from a probability distribution. So what does, and probability distribution is a joint probability distribution of XY. I'm saying it with curly D. So what does a probability distribution mean here? Suppose you want to build a image classification system. Suppose you want to just classify between cats and dogs images, right? So there are just two classes. Many people have clicked images of cats and dogs. So depending on the choice or the likingness of the persons of cats or dogs or many other, say, different factors, people tend to take more images of cats. So the probability distribution actually gives that if you randomly or not, this is not the random sample part. So if you take, with what probability you will get cat images if you just in your training data in XY. That is, what is the probability? It is parallel to what is the with what probability people take say cat images compared to dog images. Now the thing is that in the ideal world or in real world, it is not comprised of only two class. So there are many objects, and there can be many. The data can have many classes. So you might need to study a classification system with different classes. The ImageNet dataset has 1,000 classes, but of course the world is not limited to 1,000 objects itself. So the probability distribution, this joint probability distribution gives you, or not gives you, it gives the probability with which these XYs come, or right, like the data is generated. I think the more apt term is generated. So you are getting some training data, but how, with what probability the data is generated. So you can take it for the purpose of understanding that, say, for an image classification system, how preferred or how much is the preference for taking an image of one particular class compared to the others. Now, let the neural network learns the output functions as GDX. Now, why I am telling it as say D, I'll come. So GX is basically the prediction corresponding to X. So corresponding to X, Y is the ground truth and GX is the prediction. Now, if you train your model on this distribution D, data taken from this distribution D, then it is just subscripted with this, superscripted with this D letter. So if you basically, so going back to the objective or the cost function formulation, the loss is okay. So the loss is another term that we use. So cost, risk, or loss, they mean the same thing, and it is some sort of a measurement of how good or how bad your system is. So let us denote it as a function L. So it's of course a function between this and this. So this is what you want to achieve and this is what you are getting. So how, if they are exactly same, then L is 0. And if it is not, then L will have some positive value. So we will not go into the exact forms of this. These will come later. But just for the purpose of this topic, think that this is like minimum 0 when the GX, that is GDX, and Y, they match. Unless if they don't match, that is your prediction is far off from or off from your ground truth, then it has some positive value. So what we want to minimize is this L. That is, we want to have, yeah. Somebody has some question.
Can you explain once again what role D plays in calculating Gx?
In terms of what?
What role D function plays in calculating Gx?
Yeah, it is not D function. So D is just a probability distribution, and Gx plays. Okay, so if the distribution is different, the distribution that is, let's say, some other creature arrived in world which is more attractive than cat, so people will tend to take more picture of that, or say, let's not go into some other creature, maybe it's cats and dogs. So somehow people tend to change their preference, and rather than taking cats images more, they now take dogs images more, so that D will change. Okay, so depending on what I mean, in from the world. So this is the kind of world population of your images. So the world population of images, or in the world population, how the cat and dog proportion change, depending on that, your GDX may change, because the data on which it is getting trained, it is getting changed, right? So the model, you can get different model. That's it. So depending on D, that is depending on your training data distribution, you can get different predictions. So for the same X, if you have, I mean, maybe trained it when that dog proportion was not more, it would give you some GDX value, say GD1X. When it changed, it can give GD to X. Now these two can be different. That's why this superscript is given. Does that answer your question?
Yes, sir. Thank you.
Okay. Now, yeah.
Generally, in training data, we have input data and output. Here we are having input data, and outputs probability, right? Here we have three entries, right?
No, not output probability. Not output probability. I mean, the input data and output data means input and the output label, or in case of say language translation, it is, say, the input sentence and output sentence, and so your training data does not have any probability on the input output, right? The probability is the joint distribution of X and Y. So out of all images, how much portion is cat images, how much portion is dog images. So that is like coming de facto. I mean, it is not used in this tuple or in the training. It is used in a different sense. That is what the next thing that will come. I mean, ideally we should use it, but we cannot. We are not able to do it. So that will come. Does that answer your question a bit?
Yes. If you give one numerical example, maybe it will give more clarity.
Yeah. Let us go ahead with it. Let us see. Okay. So yeah, somebody else have any other question? Okay, let us go ahead. So we want to minimize the expected risk. This is the loss we have told. And what is expected risk? It is as defined, or what it literally means. So risk, loss, and cost function, they are used interchangeably, as I said. So basically expectation of the loss function, right? So, or expectation of this loss, that is the expected risk. And for expectation, you need a probability, right? So I am telling it from this perspective. The other way around also I will tell. So the to minimize the expected risk, you need the expectation, and for expectation you need the probability, right? So this is what literally it means. So it is the expectation of this L with respect to the probability. So this notation is a little convoluted, but what you can take it as this d of xy, that basically means pxy d of xy. So this is just a different notation. So this is basically the expectation of this L function with respect to this D, right? And what does it mean? That if, say, your cat image probability is, cat image probability means getting a cat image if you just say randomly take one image from your world of images. Okay, so you have millions of, say, cats and dogs images, and in the training set, suppose you want to include 1,000 images randomly sampled. So if actually in that million images 90% is the probability of cat images, say so 0.9 million images are of cat, then in your 1,000 images you can expect that 900 images will be coming corresponding to the cat image, right, in the training data itself. Okay, so you would like to reduce the loss function more for these cat images because it is coming more. So in the test function, your test data, that also comes from that million images, right? So that is your world of images. So you can expect that most of the images will be of cat. So I would be more doomed if I try to make it a good dog classifier but bad cat classifier. So does it at least connect to why we need a distribution here, or why we are thinking of the distribution? So I said, again, just to summarize, just say last 2-3 minutes, I said that I need to minimize the expected risk. So for expectation or to find the expectation of the risk, we need to have the probability distribution. And then the very last, I told why we need expected risk, because in expectation, what we are getting, the class, what we are getting more from the world of your images, from the dictionary of your images, we want to be comfortable, we want to be more good in classifying that images. Maybe there is a third class, say, ant images, and there's maybe very small percentage of ant images, say, compared to cats and dogs. So out of 1 million, say, you get 10 images of ants. Okay, so you don't care much if you are doing bad on ant images in test. So you care, of course, but maybe not more than cats and dogs. That's where this weighing of this with this probability. So this, as I said, it is not P, that dxy. I mean, D is, I mean, I have just used following some standard notation. You can think that this is pxy. Okay, so this d dxy, this one is this pxy dx dy, right? So this is giving the weight to the L. Is it somewhat does it somewhat answer your question, whoever asked the last question?
Yes.
Okay, let us go ahead and it will be much more clear also. So if we could minimize
sir, but why do we need to minimize the expected risk? What would have been the problem if we just minimize the loss function?
Sorry, can you be please a bit louder?
What would have been the problem if we just minimize the loss function?
The loss function, yeah. So by loss function, suppose you have 1,000 images, as I said, right? So you would just try to minimize the loss function for each of them. So how can you combine? So that is that this answer, that all these 1,000 images, how can you combine them? So whether you combine it with weighted summation or just individual, just average. So it is saying that the combination average is also a weighted summation where the weights are all same. Then your summation is also a weighted summation where the weights is equal to 1 for all of them. So what this is saying is that you weigh your loss function coming from each of the training pairs with the corresponding probability. What probability? What the probability of getting that image in the world population, right? So did you get the problem? I mean, what
yes.
And what I exactly said, it will come in the probably the next bullet point, the summation thing. So if we could minimize the risk, we would have got the true optimal function. So if we could minimize this, I am saying we could. So why I'm saying we could, that will also be a little clear in this slide itself. So if we could minimize this, we would have got the true optimal function. What do we mean by the true optimal function? So this, let's see when we are minimizing this, then we are getting, I mean, we are just minimizing this thing. So I mean, this expression only takes this loss function and or the objective rather, and basically finds the arg minimize. So what is the true optimal function? That is the function that generates y from x. That is a true one that we can get, but we don't know the actual distribution. To minimize this, we need to compute this, and I mean, to minimize this, we need to compute this, and to compute this, we need to have this. So we don't know like what actually dictates to take people cat images more. We don't know. Maybe the images that you get as your training set, whether I mean, it comes from a population, part of the population where actually say dogs are like more. You don't know basically. So what is this generating function, this distribution? So so that we actually minimize the so, but we don't know the actual that generates that. So what we actually minimize is the empirical risk. So what basically it tells is that we would have liked to minimize this, but we are, I mean, this means an expectation. For to get the true value of the expectation, you need to know the true probability, but you don't know the true probability. So what you resort to, basic probability says that you just take sample and do the empirical evaluation. So if you don't know the expectation of a probability distribution, you sample from it and just average, take the average. So that's how you compute the, say, probability of heads and tail in a simple example of a what is that, Bernoulli distribution. So here also the same thing. So this comes with that Monte Carlo philosophy, that you are getting the average or the expectation. So we use this term expectation and average interchangeably, but there lies this philosophy that basically average is the empirically computed expectation. So, and what does it tell? That to, okay, let me just use another color. To compute this expectation, that is this part, you need to first sample, that is you take these n samples from the same distribution, and then you compute these L functions for all these in examples. So L are computed on xi, I mean all these i's, and then you average it. So that's that gives you approximated value of this true expectation. And why does it work? Because it has some I mean not rigorous, but some derivation which basically involves that delta function and so on. But I'm not going into that. But the intuition is that when you sample, you get I mean, when you sample your basically this training set from your population of the data, then the samples come in proportion of the actual probability. So if it is the case that in your population of images 90% is cat, then in your training samples, if you are sampling say 1,000 images, then 90% will be cat images. So having that assumption, I mean this is a good approximation of the actual expected risk, or any for any expectation. So but that will only be true by law of large numbers if you sample a lot. So we don't get the true optimal function. Instead what we get is I mean by minimizing this empirical risk. And so this is one issue, that you don't know the true distribution. That's why you empirically evaluate this expectation. But another thing is that you minimize. So you see, you basically minimizing over this GD. So we choose a family H of candidate prediction functions and find the function that minimizes the empirical risk. So now you have computed the objective function which you need to minimize, or where you need to basically apply your minimization tricks and so on. But what function or what model do you want to minimize on? So what is the form of the model that you, or what is the form of the function? So f is the true optimal function. So I said y is equal to fx. Maybe that is the true one, you don't know. So what is the form of f? Whether it's a straight line, it's a polynomial, it's a complex neural network function, it's a SVM, it's a random forest, you don't know. They are all function approximators, right? So for even a neural network, a single neural network, I mean, it can have several different varieties. How many layers? So say in each layer, how many say neurons or filters, you don't know. So I mean, that's an exhaustive set. So what you do is you take only a few candidate probabilities. Okay, I will take out of all, say, SVM, random forest, polynomial fitting, etc. I will take only neural network, and out of them I'll try with only, say, one particular, say, ResNet architecture. So only ResNet architecture is a different kind of a function. VGGNet is a different kind of a function approximator. These names, it will come later, it will appear later when we describe more on the architectures. But even with the ResNet, how many layers, how many in each layer, how many say ResNet blocks, whether they will be different in different layers. So you can only try a handful of them. So that is what is given by this family of the candidate functions. The candidates, you cannot do this exhaustively, and find the function that minimizes the empirical risk. So your GD is constrained to be inside a family of functions. So you would have liked to basically minimize this. What you are actually minimizing is this, and that too in a constraint scenario. So that is where the risks, I mean, different errors will creep in, we'll see. There is an in-between thing also. So what we would have liked is this, and then these are the two limiting factors. For that, we are approximating it. One is, of course, we don't know the true data distribution. The second is we are constraining ourselves to a limited set of functions. The third is, or rather in-between thing, is that we don't, I mean, somehow say we know how, or somehow we know that the true distribution. In that case, we can also try to constrain. So since F may not be found in the family of H, we also define this. Let us define it and see what are the conditions and so on. So this we are just telling at G H star D. So it is argmin of EGD for GD in H. So just to summarize this slide, we want to minimize, I mean, would have ideally liked to minimize this, but we minimize this where you are constrained in a different functions family, and I mean, a limited family of the function, and you don't know the true data distribution. Here is what we would have gotten if we would have known the true data distribution. So let us go to the next slide, and then I'll stop for questions. So this is the source of error. Okay, this is sources of error. So there are two limiting assumptions that are kind of limiting us. One is true data, whether true data distribution is known or not, and whether the family of functions are exhaustive or not. So when we get F, or if we want to, I mean, what F does, rather say, it minimizes the expected risk. So what was expected risk? This one, right? And we get F if we can minimize it. So no constraints on function family. So F minimizes expected risk, staying within like the unconstrained family of functions, the exhaustive family of functions. So the assumptions are true, data distribution known, and family of functions are exhaustive. So this is just summarizing the last slides once more. GDH star, this is the last thing that we discussed. So here, right? So, so it also minimizes the expected risk. As I said, it is the in-between thing. But staying within a family of function that you choose, that is dependent on the expertise. Okay, you have other ways also. You have a held out validation set. You try to choose the architectures, the hyperparameters of the architectures. Hyperparameter means it's not parameter, it's less than parameters, but it is important. That is, say the number of layers, what is the nodes, etc., etc. So staying within that family of functions. So here the assumption is that true data distribution is known, of course, because you are trying to minimize expected risk, and family of functions not exhaustive. Then you actually relax both the assumptions, that is true data distribution not known and family of functions not exhaustive. And that is what we do, because these assumptions are true. So this minimizes the empirical risks, staying within the family of functions H. So these are the two most limiting functions. And another thing is, not to forget, we rely on a surrogate loss in place of the true classification error rate. So I did not discuss it much, but just on a high level thought, what it means is that what we would have liked, for example, in a image classification scenario, is we would have liked to say that L function. So it is concerned with that L function. It can be the accuracy, but we will see that the accuracy is not a continuous function. So we will basically go into another thing, cross entropy loss, etc., for classification. When we do that, we will come into that. But so that is not exactly what we would like to minimize, because it is discontinuous, the accuracy. And I mean, this is just one example. There are other losses. So because it is discontinuous, it cannot be efficiently, or it cannot be actually minimized using a gradient based optimization technique. So we have told that here in the first slide, that gradient based optimization is the most popular way. So where this evolutionary or derivative pre-optimization comes into picture. But yeah, we will not go into that. So let me actually stop for some questions, and I'll just take 5 more minutes, because I thought of covering a lot more today, but we did not get time. Any questions on this part? Not going.
Sir, in empirical calculation, we assume that the probability of each data sample is equal.
No, this is a subtle catch you need to understand. So what we do is that, I mean, just try to think about that 90% scenario that I told you. So if you have actually in your world 90% probability that a cat image exists out of all images, that is cats and dog images. So when you sample these n images from that population, it will be 90 images of say 1000 images you have sampled. So 900 images of cat and 100 images of dog. So when you sum it, you are summing 900 cat losses and 100 dog losses. So it's not equal probability, right? So that is where the catch is. That's why it works, at least to some degree of approximation. So though you are summing them individually, 900 sums and 100 sums, 900 of dog and 100 of cat, they are separately just added, but you are ultimately getting 900 cat images, because 90% is the probability of getting cat images, right? So that's why this Monte Carlo approximation, they work. And I mean, it will work, I mean, perfectly if you had I mean it will work better as you get more and more training data. More as you sample more and more training data. So 1000, if that 1000 you increase to 10,000 or even 50,000, that will be this 90% proportion will be more close in that case. So is it clear someone?
Yeah, sir, but there is another doubt. Then we can, it means the empirical distribution is calculated independent of the probability distribution.
No, it is dependent. That's what I said. Empirical distribution, though I did not tell the term empirical distribution, but still I'm just trying to answer in terms of empirical distribution. So if you have infinite sample, then of course empirical distribution is same as the actual probability distribution. But to some approximation, the small sample or low sample approximation, it is to some extent close to the actual distribution, right?
Okay, sir.
Sir, in point number 5.
Yeah.
Hello, I'm audible, sir?
Yeah.
Sir, in point number 5, we said that expectation is equals to the average, 1 upon n summation. In this case, sir, there is some limit to this, because we are saying that this training data completely describes the universal set. But if that is not the case, we can't write this equation, right?
Yes. See, if what I don't know if you are meaning that I should write approximate, right? You are saying not equal to but approximate.
No, sir, means this should not hold every time, because we have, in this case, we are assuming that our training data is sufficient to represent the universe.
No,
means
see,
no, not that case.
See, you are making one sum, or you are ignoring one fact. These are two different things. This is EGD, this is ENGD. So I'm not saying that they are same. I'm not saying they are same. What I'm saying is that we should have minimized this risk, but we are minimizing this. I'm not saying never that EGD is equal to ENGD. Does that answer your question?
No, sir. Actually, I'm confused. So.
Okay. I mean, I will not go into the next slides. Maybe you can try to explain what is your confusion.
So means when we are writing this expectation, and this means we are writing expectation because we have assumed some distribution, but that distribution or is not. See, the distribution we are defining is with respect to training data, not with respect to the complete data, sir.
Which distribution you are telling?
Sir, this dx comma y.
Yeah, this is not with respect to the training data. This is with respect to the world population of data.
Okay, sir. I thought it was with respect to the training data where we got.
No. Training data is the sample set from that, right?
But sir, we will estimate this using only training data, right?
Yeah, that's why these two are different, EGD and ENGD. What we are estimating on depending on the training data, that risk I am denoting as ENGD.
And sir, you are saying that we are estimating it using the training data. Dx comma y is estimated using training data. But if training data
is y, no. Dx comma y is not estimated. This is the true data. It's not an estimated distribution.
Okay.
It's a true probability distribution.
Okay, that we don't know.
Okay,
got it, sir.
Okay.
Yes.
Let me take this opportunity to at least go into 2 more slides, because we have like miserably failed to move ahead. Just 2 more slides. So a simple learning problem. So let us go ahead with say 2 data points and 2 hypothesis sets. What I mean by this is that you have a 2-dimensional problem, a regression problem. You have X, you want to find Y. Okay. Now this is the blue curve is true data distribution point. So for different X, this should be the Y's. But we have only 2 data. So this is kind of the true distribution or true data generating function, these blue plots. But when you sampled, you are getting just 2, because your training data set is composed of n equal to 2. So once you sample, you have got these 2. When next time you will sample, maybe you will get, say, these 2. It can happen, right? So let's not go into this red ones. Let's just think about this. Similarly, the same data here. Now this is like the n value. N is equal to 2. Okay, now, okay, let me actually go back to blue, just so that you are not confused with the color coding. And suppose the two family functions are this, hx is equal to b and hx is equal to ax plus b. That is the hypothesis that y is generated from a straight line data that is parallel to x-axis, and y is another straight line which is in the slope intercept from. That is my candidate functions. It is not at all the true dxy. I mean, here it is not dxy, but the f, what I should say is f. It is not the true f that is generating the data, which is the blue function. But what I'm trying to come is that the limiting factors that I told. So instead of all these data, first of all, I am just having two. Okay. And the first and the second thing is, instead of all different other hypothesis functions, maybe sine, cosine, tan, maybe e to the power, maybe polynomial. No, I'm just limiting myself to two different hypothesis functions. Then what will happen? If you have these two data and if your hypothesis is this H0, then you will get this straight line. I mean, you only have these two data, so you just take the average. I mean, this is what your hypothesis allows you to have. And for this hypothesis, you know, there are 2 points, so you can fit a straight line which will pass through these two points. But it is, I mean, neither of these two is very close to what the original function that is generated. Now the next slide, which is last. So let's repeat this experiment many times, and that's what I was telling, that for say these two data sets, sorry, these two data, or I think that was already we considered. So maybe let's say this is the two samples. These are the two samples that we got. So maybe this line is what you have got. Now for the same two data, maybe the straight line that is gotten is this, right? So you can get, as you sample as different person, you can think that sample different training data. So you can think of it as there are lots of unlabeled images of cats and dogs. You are asked to build a cat dog classifier. You are just sampling few images. In that case, just n is equal to 2. You are getting these two. Your friend is getting, say, these two. Just randomly sample. His friend is getting these two, and so on. So all of you will get different prediction function. I mean the model, the trained model, right? So you are getting this, your friend is getting this, his friend is getting this, and so on. For H0, for H1, say you are getting that your friend is getting, say, this, his friend is getting this, and so on. So for each data set D, you get different GDN. So I think it also comes back to the other some question that was asked earlier. And for a fixed X, GDN X is random value depending on D. So for a fixed X, it will give you some value, this value for your model. It will give this value for your friend's model. It will give, say, this value for your friend's friend model or friend's model. So, and similarly for this hypothesis also. So depending on what randomly data you sampled, for a fixed X, your GDN X is a random value depending on D. So this GDN X is a random variable. So that, I mean, with that, I am leaving, but yeah, I expected to cover at least 5-6 more slides. I might be needing to do it a little more speedily next time. But yeah, if you have any questions, and I'll start the office hours next Tuesday, 6 p.m. So if you have any questions which may be that you are confused, so that the pace of the class does not hamper much, please come to that office hours. I mean, the link will remain same. So I'll make an announcement after I induct you guys into Piazza. I think today is the last day of registration, so hopefully the registration will be finalized. Any questions?
Hello, sir.
Yeah.
What is said?
Yeah.
Sir, actually, we define a family of function that is H. Is it predefined, or we have to calculate that, or we have to calculate by seeing the how training set goes on?
See, this is a question that comes from expertise. So you need to draw parallel to what you do as a machine learning practitioner. So as I said, these H things, if you are familiar with, of course, machine learning is a prerequisite for this course. So if you are familiar with machine learning models, so you have training data and you need to take decision whether you, you would like to have for a neural network. First of all, whether you will go ahead with a neural network. You can go ahead with SVM, you can go ahead with Bayes classifier, logistic regression. So that is the family of function. That is one component of choosing what family, what functions will come into your H set. Okay, so in H, the first function is that, okay, I want to have an SVM with say these many parameters. I want to have a random forest with say 5 trees. Each of the trees will have a depth 4, so on, and so many nodes. The next family of function is one neural network, which is a fully connected neural network, 5 layers. Each layer will have 10 nodes with say 10H activation function. Next family of function, again 5-layer neural network. The first one will have 5 nodes, second one will have 10, third one will have 12. With first one will have 10H, second one will have say ReLU, and so on. So this is what I mean by taking different H. You cannot do it exhaustively, right? So if you could have done, if we have infinite computing power, you could have done that. So you need to resort yourself to some constraint, and you may ask, like, how can I know? And that is where the expertise comes in. People have seen that, okay, in this type of data, this worked well, so you can try with that, a slight perturbation, a slight variation of that. You have the validation data for that. That is, you just keep one small held out data, and whatever family of functions you have chosen, out of them, which one works best, you can at least get some idea. So the basic take home message is that you cannot start, you cannot examine exhaustively all family of functions. Okay. Anything else from anybody?
So I'm confused about something.
Yeah, please.
Like here in this diagram, if we choose any 2 points from the blue circles that you have drawn, I think they are
your voice
points
is breaking. Your voice is breaking. The last part I did. If you choose any 2 points, then what?
From the blue circles that you have drawn in this graph.
So
I think they are different examples of training examples, but
yes,
the distribution function still remains the same, right?
Yes, distribution function remains the same. I mean, it is, you need to, I mean, I'm just trying to clarify. I'm not sure whether you are also meaning the same or not, that this is say x1 and this is x2. I mean, that is xi. So I don't know how to undo these things, but yeah. So this is say x1 and this is say x2. Okay. Now this x1 and x2 is in one training set. I have not denoted any training set here, but say this is T1. So T1 is x1, y1 and x2, y2. Your friend is taking another training set where he is taking, okay, let me actually tell it as x1 or again. Okay, let me just cross it. So let me first tell T1. T1 is x1, y1, x2, y2, but it is for T1, for T1, for T1, for T1. T2 is again x1, y1. So this is x1 T1, this is x2 T1, this is x1 T2, this is x2 T2, T2. So T2 is X1, T2, Y1, T2, X1, X2, T2, Y2, T2. So both are X1 and Y1, but this appears in your training set, this appears in your friend's training set. So I just wanted to clarify if you are meaning this. Now you can ask what your question is, confusion is.
Yes, sir. So based on these two different training sets, my friend is getting some other GN and I am getting some other GN.
Exactly.
Irrespective of my function D, of my probability distribution D, right?
Irrespective of not your probability distribution, irrespective of the true probability distribution.
Yes. So like I was confused because the bullet point has got no relation with this diagram, right?
Why no relation?
Because in the bullet point, it says that when I change my D, you get a different G and D.
Yes, yes, D is different. So D is the, yeah, I think maybe the notation is a little confusing here. So yeah, each data set D. So or rather it is, yeah, so DXY and D, maybe you can think as different. So maybe you can use there as P. It will be better to use P, the DXY. So D is, so what I have told as P is D here. Okay.
Yes.
Anything else? Okay, let me complete this then. Yeah, again, I have to go a little bit faster from next time. Otherwise, we will not come to deep learning even. Anyway, thank you, and we will meet again on Wednesday.